Hello students, in this video we'll discuss the spherical wave equation. Let's recall the wave equation in our n cross r is, you can say r plus if you want, is utt is equal to c squared Laplacian u, okay? And so now what we want to do is we want to say, okay, well, in this case over here, the Laplacian is just the sum of these derivatives, right? So over here, Laplacian is just going to be d1 squared all the way down to dn squared, like that. And we're going to focus on a special case. We're going to focus on the case when n is equal to 3 in 3 dimensions. We have utt is equal to c squared uxx plus uyy plus uzz. And then we note that the Laplacian can be written in spherical coordinates. So we're going to write this in spherical coordinates as c squared, and then urr plus 2 over r ur, and then plus angular derivative terms, angular derivatives. Okay, we have a video for the exact formula. For this video, we don't need to know the exact formula of the angular derivatives, because we're going to look for solutions now. So look for solutions of the form u of r, theta, and phi are just u of r, i.e. u theta equals u phi equals 0. There's no angular dependence on this function, okay? So there we have it. So we're looking for radial solutions of the wave equation, right? And so now, of course, what does our wave equation become? So our equation becomes the following. Our new wave equation is going to be utt is going to be equal to utt is equal to c squared urr plus 2 over r ur. Okay? Now to analyze this problem over here, let's make that look a little bit nicer. Let's say utt. So that's utt. Okay? And so to make this look a little bit nicer, what we're going to do is the following. We're going to let v be ru, or u is equal to v over r. Okay, so we're going to look for solutions in this auxiliary form over here. Okay, so if this is the case, what will utt be? Utt is just going to be vtt over r. Easy enough. Now let's do the r derivatives over here. The r derivatives are next. So what are the r derivatives? So if I do a ur is going to be vr over r minus v over r squared. And then urr is going to be vrr over r minus vr over r squared minus vr over r squared, and then plus 2 v over r cubed, like that. So if we put these together, we look at urr plus 2 over r ur, what are we going to get? We're going to get that this is going to be equal to what? This is going to be, urr is going to be vrr over r minus 2vr over r squared, and then plus 2v over r cubed. Okay? And then what is 2r times ur? 2r times ur is going to be what? 2r times this thing over here is going to be 2vr over r squared. Okay? And this thing over here is going to be negative 2v over r cubed. So this term cancels with this term, and this term cancels with this term, and therefore we get that this is just equal to, so hence this implies that urr plus 2 over r ur is equal to vrr over r. Okay? That's how it translates. So now what does our wave equation look like? So our wave equation in these other variables now becomes the following. It becomes what? utt, but utt is what? Utt is vtt over r is equal to c squared, and then vrr over r, vrr over r. Okay? The r's cancel out, and therefore we have vtt is equal to c squared vrr. In other words, v satisfies the one-dimensional wave equation. V satisfies the 1D wave equation. Beautiful. Okay. And so now by D'Alembert formula, implies that v of r and t is going to be an arbitrary function phi of r minus ct plus another function psi of r plus ct, right? And now I know that u is equal to v over r, right? So now that tells me what u is. So my spherical waves, so our spherical waves have the following form. Our spherical waves have what form? They have the form u of r and t is phi of r minus ct plus psi of r plus ct, all divided by r. So there's this radial decay. There's this decay as r gets very large. These solutions tend to dampen out, right? So this decays for compactly supported functions phi and psi. So just note if phi and psi are compactly supported, then there's decay as r goes to infinity. In further videos, what we'll do is we'll study the wave equation when there's also angular dependence on these things, because those are in some sense even more interesting, right, when there's angular dependence. But these spherical waves reduce to the one-dimensional wave equation, and from there, you can actually get an exact formula if you have the initial conditions. If you have initial position and initial velocity, you can use this formula over here and use D'Alembert formula to find exactly what the solutions of the spherical wave equation are. Thank you very much.